Hello. Alright. Gonna see if we can improve this performance. Now, to remind everybody where we're at, this is basically the same thing I said last time. We have our SPH rendering. When it comes up, everything looks fine. Pretty good refresh rate. It's rendering all the particles in this simulation. The size of each particle is proportional to what's called the smoothing length of that particle. Now, I don't think I have it exactly right, but it's probably within a factor of 2 correct. When we zoom way in, you'll see the refresh speed. And here, let me emphasize this with the color bounds. The refresh speed goes way down. I measured this with the Insight debugger, and I was seeing a drop in frame rate of a factor of 4 or something like that. So let's see if we can figure out why it is that way. I have some suspicions, as I shared last time. What I think is going on is I think that as we move in, each one of these quads becomes considerably larger. And they're not actually quads, they are quadrilaterals approximated by, well, not approximated, they're quadrilaterals that have been rendered as a triangle strip, so a total of 4 vertices. Let me make sure. I've got this funny thing with my headphones that, yeah, it looks like desktop audio is turned off. Good. Okay. If they don't get activity for some stretch of time, they turn off. So I'm going to turn on some music on my end, but it looks like it is not going through, so that's good. Each one of these is a quadrilateral that has been rendered. So rendered via a triangle strip. As we get closer, the perceived size of each triangle strip or quadrilateral gets much, much bigger. And that, I think, is what's happening. It's a problem that I've heard described as fill rate or raster rate limitation. So we're going to see if we can get around that. Now, the very first thing I'm going to do is I'm going to demonstrate that I think this is the case by changing the max inverse. So I've set up the shader here, and let me look at this shader for you. I've set up this shader by computing the GL position. I clamp the, well, there are a couple different stages here. So imagine we have a particle. We know how big in world coordinates that particle is supposed to be. I don't want to pass in too many pieces of data. I just want to pass in its position and its radius. And then we're going to instance render a triangle strip based on that. So what I do is I take the position, I add on v radius. So that gets us a position in world space, because the v radius here is going to be, or I'm sorry, this gets us a position in clip space. Does it? Wait a second. Let me think through this for a second. Yeah, okay. Position here is going to be -1 or 1. So in both x and y. So we first construct, we take our inverse projection model view matrix, and we multiply that by our model vertex, and then some clip position, in ZW. Model vertex here is going to be an in vec2, so -1 or 1. I have really confused myself. Yeah, okay. So the output of, and see, I said stumbling around because that's what I'm doing. The output of multiplying the inverse projection model view matrix times a 4 vector composed of the model vertex, which is in clip space, with the clip position in ZW, should give us the vector necessary to move by a given set of in the direction -1, -1, or +1, +1, or +1, +1, -1, or -1, +1. So by adding our radius times this normalized vector, we should now have a world space coordinate that corresponds to each one of our 4 corners of the quadrilateral, representing our sort of the billboard projection of this particle. That billboard projection is going to be orthogonal to the viewing plane. So the next thing that I do is I take this I clamp our position based on our clip position minus our maximum particle size over 2, which max particle size here is 1 over this, and our clip position plus max particle size over 2. So where this gets us is it gets us so that our max particle size constrains the ratio of our viewing window to the largest particle. So if we set this to 104, we actually see a considerable improvement, because now the largest billboard size is 1/100th of the screen. So since this is now reasonably interactive, it likely means that our rasterization is the real problem. So I want to experiment and figure out if that really is the problem. So what we're going to try is we're going to say vec4 temp position equals GL position I'm going to, instead of doing clamp on this, we're just going to make it the way that it is, and this will be vec4 temp position. And so if temp position dot x is less than clip pos, oh here, let's see, if temp position x is less than clip pos minus max particle size over 2.0. This was something I tried the other day. Let's see if I can make it work any better this time. Or temp position dot y is less than clip pos minus max particle size over 2.0. Or now we'll do this greater than. In this particular case, we're going to set our clip. We're going to set GL position.zw equals minus 100. That should effectively move us outside of anything that will be displayed on screen. So the end result of this should be that we essentially discard that vertex and that set of vertices. Now, this should be true identically for all 4 of the coordinates. So let's see if this works for us. Now let's also just do an else here, and this is where we'll do rest of it. UV equals model vertex. So let's see what happens if we recompile shader. Oh yes. Let's see. Line 70. Looks like vec4 temp position. Oh yeah, I did this the other day too, where I didn't have the exact right number of coordinates. Or the exact right number of brackets. Syntax error, unexpected. Huh. Vec4 model vertex. Do I have the line number wrong? Oh, implicit cast from int to vec2. That's on line 76. Recompile again. I'm still getting the vec4 temp position equals projection times model view times. Oh, yes, I do need another parenthesis. Okay. And now this time, let's see what the problem is. Invalid operands to less than. Temp position x is less than clip pos dot x. And now I'm sure there are better ways to do this. But I'm just going to go ahead with what I know is going to get us there. So let's recompile our shader once more. Wow, that's something. So where did I go wrong? Okay, so now let's take a look. What we actually want to do is we want to figure out if it covers the entire screen. So if it covers the entire screen, that would be equivalent to the min and the max. Actually, vec2 of minus 100, maybe that's the problem. GL position equals vec4 minus 1000. Maybe that'll do it. Nope. So in this case, it's no longer rendering them. So that's interesting. It's still not getting that great of performance. So let's take a look. How can we discard? So GL position, let's say we will make our V radius equal 0.0. That'll actually be a bit of a simpler solution, I think, because now each point will just be 0. So if we recompile the shader, our V radius is going to be equal to 0. Let's make our V radius really small, but not exactly 0. Still not getting very good performance. So let's try another trick. I just want to see the particles that are not small enough. So let's set a flat out use particle. We'll say flat out float use particle. We will not modify any of this. We'll just say use particle equals 0.0. inside our fragment shader. I'm going to close this up. We're going to say in float use particle if use particle greater than 0.0 and it's flat. So let's make sure we've got in flat in discard. So now what this should do is it shouldn't change any of our items here. But what it'll do use particle equals 1.0. Let's just set this right there. Oops. If it's less than 0.5, discard it. So in this case now, you'll see we're getting a little bit better frame rate. Still not that amazing. Let's take a look at this. Temp position X is less than that. Let's go ahead and try this out for all four. So we actually now want to know what the clip space pause. So our temp position is going to be projection times model view times vec2 or vec4 yeah vec4. So remember that what we've got here is we've got our model vertex. Our model vertex comes in, it's a vec2. It's going to be -1, 1, or between, it'll be -1 and 1, but permuted across all four. So we'll do temp pos to model view times vec4 of our position, which is the vertex of our model. But here we actually really only care about. Yeah, so this is, in fact, it's using an SPH smoothing kernel. But what I'm trying to eliminate is I'm trying to eliminate the super slowness here when I zoom way in. And the slowness comes from having really big areas of the screen to fill, is my understanding. So let's see if we can figure out how to get around that. Basically, if the size of our triangle strips, let's try this. Yeah, that doesn't really help. So if the size of our triangle strips is going to be greater than 1/10 of the screen or something like that, so this is if we only have the particles that are one. This doesn't actually change our size at all. What it's doing is it's filtering out all of the low density particles, which oddly enough are the ones that shouldn't contribute very much to our rendering, except as an offset, but that do. So you see that when I turn off all those low density particles, we get a much, much better and more interactive refresh rate. Now, you'll note that I've done a bunch of funky things here, so we're not really seeing it is a little bit messed up. So don't worry too much about that, because when I get rid of the this filtering, it's going to go away. So we're left with a couple things here. We have this problem where we have large areas that have offsets from a bunch of particles that are really small, or really big, but that don't actually have that much of an impact. And if I reverse this, you can see what that looks like. These are all of our low density particles. They've got really big smoothing lengths, and they've got really big smoothing lengths, and they do contribute, but you'll note that they really don't have that much in the way of dynamic range. So let's take a look. How might we fix that? Let's get rid of all this. Let's recompile our shader. Use particle equals 1.0. So this is our same shader, but with everything turned on. All of our little particles, all of our big particles. So I've thought about different ways that we could potentially address this, but before we can really do any of them, we need to have a way of figuring out how big this billboard is going to be. So let's do this. Temp pause. We're going to set up a set of 4 vec4s. So vec4 temp position. And we're going to say vec2 left corner, right corner. So our first temp position is going to be for our upper left corner. And in this particular case, what we need to modify is our model vertex. So here this will be -1, -1. And our left corner is going to be temp position.xy. And we can actually, you know what? Left corner is equal to this dot xy. And now our right corner is going to be the exact same thing, but for 1, 1. And really it doesn't matter if either left or right or whatever. So we're going to say vec2 size is equal to the absolute of right corner minus left corner. And so anytime size less size dot x less than greater than, let's say 1, the size maximum should be about 2, or should be exactly 2. So we're going to say use particle is equal to size x less than 1 times size dot y less than 1. So only in the case that both of those things are true, so if it takes up less than half the screen, it will use the particle. Actually, let's see, that's probably going to give us an error, so let's do I think that'll do it. Recompile the shader. So let's say size x less than 0.2, size y less than 0.2. Okay, so now we've got the distance from the right corner to the left corner. Oh. Undefined variable dist. I think it's distance. There we go. So now it should only be rendering when the distance. Let's do this float. Just do use particle. And so what we're doing here is we are computing the distance from the right corner, which should be this. So the model view times the v radius, yeah. So use particle is a float of the distance less than 10th. No, let's say 100th. Okay, so now it's correctly cutting stuff out. Looks like I'm getting weird half cut out. No, maybe not. Those look all right. Now if I zoom way out, they should all show up. But so it's now computing the distance from the left corner to the right corner, and if that distance, which is in clip space, is less than 10%, we should see that. We should see the images, or see the particles rendered. When we zoom in, it should get even better. Now we're doing a couple extra matrix multiplies here. I'm sure there's a way to compute the linear algebra, the commutative properties and all that stuff in order to make it faster, but let's just take a look at this. So we're not seeing huge performance improvements yet. We are seeing things get cut off at the very edges, or get cut off when we go in, but that could also be accomplished with a different clipping plane. It does overall seem to be giving us better performance. One reason that we might want to change this up a little bit is because it's still calling the fragment shader for all these different things, and so we might be able to eliminate some of that by discarding a vertex somehow here. So in principle, we should be able to actually, you know what? If we set a degenerate vertex, it should work. So instead, let's set v radius times equal use particle. So now we should end up with a bunch of degenerate vertices. they don't even get passed on. Now I should now be able to comment out this, and it produces the same result. Okay, so now in this case, as we zoom in, let's see. No, let's try 0, 1. Yeah, in this case, it's much more performant. And if we comment this out, so this is what it looks like right now. Let's comment that out. That's without the discard. Let's get the discard back in. It's still quite slow because the process of rasterizing and passing the fragment shader on is causing us a fair bit of lag. So that's interesting. And it kind of makes me wonder if this would be well suited to, say, a multi-pass rendering, which I'm not really equipped to do. That's not really in my wheelhouse. But we could do a level of detail rendering where all the particles with really big smoothing lengths, or at least apparent size, get rendered in the first pass. And they get rendered at a lower resolution and then interpolated up. But that still might not help that much. I guess the other thing that's possible would be to attempt to identify a consolidated particle whenever you have multiple large smoothing length particles that are near each other within some level of detail. Now that also strikes me as something that'd be really tricky. So what I'm starting to think instead is that we will not do any clamping. And instead use this to filter out yeah, there we go. And now that lets us prototype our viz using just the high density particles, for instance. And then when we want a production image, we can drop the max inverse back down. So I'm getting reasonably happy with that notion. I think that's actually what I want to go with. So let's implement that. Now, one of the first things we want to do is I want to go back over here to our particle rendering. So particles.py. And I want to change this max inverse fractional size to a filter. So we'll do ngui.text. And we will just say GUI. Let's take a look. We're going to use Dear I Am GUI in this. Let's see, text, yes. Text. Filter, particle, max size. And then this will just say no text. We're going to set it to 1/self.particle max size. we're going to just go from 1 to 100. And actually, you know what? All that printing of stuff, I really don't like. So let's see if I can figure out where that print is coming from. Looks like... Huh. Yeah, I have no idea where that's coming from. Should be in one of the events. Let's take a look at our Piglet context. On mouse press, on mouse drag, on mouse scroll, on key press. Oh, I do have some Python code in here. I told Clement that I did not. Huh. Well, I don't know where the printing's coming from, but it's coming from one of the event handlers. I did modify Piglet at one point. Maybe that's what it is. All right, let's check this again. Python examples, SPH rendering. Okay, looking good. Zoom way in, see the bad performance. Filter particles, max size. Getting the good performance. Okay. Well, that was good. So let's see. Let's stage some of our changes. SPH rendering I'll ignore for now. OpenGL support. Oh yeah, I added some map textures the other day. It should generate some textures for when we are sampling at a low resolution. Let's see, I don't need that change. Let's go to particles. Yeah, we've got our change there. So let's stage that. We've got our particle frag. Actually, before we commit this, let's go back to our vertex shader. And here we're actually going to do ignore the use particle completely. Add a comment. Let's get rid of our flat out. Let's go to our particle frag, get rid of our use particle, make sure that it still works. Okay, zoom way in. Yeah, all right. So now let's stage those changes. Let's push that up to our repository. Okay, so now we just got a nice little quality of life improvement for particle rendering. Now the next thing we need to do with particle rendering is we actually need to be able to swap out whether we're doing SPH rendering or not. We can kind of do that by using a flat curve. And I'll show what that looks like. do this, we zoom in a bit. If we go to flat, see that here each one is now just completely flat. There's no attenuation. Each one's just a circle, like a bit of water on your glasses or something. And if we switch back to cubic, you can see it like that. You can see minor changes with the other ones. I know that they are important, but I think the particular circumstances that I'm in don't really set that up. Now, one of the other things that I've been pretty interested in looking at has been improving the filtering for grid codes. So I'm going to go back here and we've got our quality of life improvements. So let's go and let's check out main. Oops. Oh, I do want to stage the OpenGL. OpenGL Sport. Let's do that. Add MIP maps for 1D textures. Let's see, blocks. I will fix that in a later one. Let's get --p. Stash that. I'll stash that, but I'm probably not going to use it again. Stash that. Okay, I'll stash that. Gotta stash that. Gotta stash that. No. Okay. So now we are at main, but with all of the quality of life improvements. We're not going to be doing particles for a little bit. We're going to go back to AMR volume rendering. So let's do Python examples AMR volume rendering. Now there are some other quality of life improvements that I would really like to see here. Like for instance, this is all now totally blocked when we're doing it. Now, this is our AMR volume rendering. See that there's no reset color map. We do have a recompile shader, but I'm gonna add some stuff to this. And you see we're also getting a whole bunch of fun lagginess here too. This is not the best frame rate. And I think part of that is that we're casting about the same number of rays, but I think that we are passing all of the vertices along even when we're not able to render a given component. So we'll take a look at that in just a moment. Now I'm going to start a new branch, create new branch, and we're going to call this AMR quality of life. So take a look over at my pull request. I'm going to just wholesale copy the reset color map. Here. Now, let's unstash all of our changes. Okay. Okay. Let's take a look at our diff. so it staged this change, staged this one, staged this one. Alright, I'm going to discard this one. I'll stash it again. And I'm going to unstage those changes. And let's discard this. Let's go over here to AMR volume rendering, or into blocks.py. We're going to go down here to recompile shader. We're going to say if in GUI button reset color bounds, reset the color bounds. Now changed equals changed, or actually, you know what? Changed equals true is fine. So now when we run it again, we'll get back here to having our color bounds. Enjoy your lunch. So we go in here, got our block rendering, and this should reset our color bounds when we zoom way in. Oh, and it does. Oh, that's great. If we go to projective integration, reset color bounds also does it. Excellent. Now let's take a look at our grid shaders. Now what we shouldn't really have any problems with here is we shouldn't have a lot of problems with the way that our grids are expanded. So we're using a geometry shader, but we don't have that many objects. So an instanced rendering shouldn't give us that much improvement over our geometry shader, I think. We can explore that at another time. But let's take a look at what we can do. So we got our V right edge, V left edge. In principle, we shouldn't be rendering anything that appears outside of our viewport. Let's make sure that that is the case. Actually, yeah. So if the left edge, the vertex left edge, so we've got this geo position times model vertex, location of the vertex in model space, grid position. Let's go to our geometry. These are our arrangements. This gives us each one of our new, it gives us our vertex, left edge, right edge. It's just passing those through. And then it emits a vertex based on the arrangement. What we should be able to do is we should be able to determine if we are outside of the grid, or if our projection is in that direction. I think, no. All right. Let's go back over to our blocks. Let's take a look at our culling facing. All right, it's culling the back faces. That's pretty good. So it's also possible tracing.frag.glsl. It's also possible that something going on in here is taking far too long. So, for instance, we've got our glfrag coordinates, so we do need to calculate that for every single one. I guess it would be interesting if we were able to use those as varying, but I guess we probably are not. Inverse projection times clip pause is the eye position. The eye position will not be the same. It will be the same for everything. The eye position should be a constant 2D texture. That doesn't help us too much here, because we're not doing so many re-renderings, I think. So we've got our direction, TL, Tmin figures out where exactly this ray hits our grid, does our floats. If T1 is less than T0, so okay, if it's on the wrong side, it discards the fragment. Should we be doing more discarding? I think we might need to. So in this particular case, we're figuring out where the ray intersects our box, if it does. So let's take a look at how we do this in the software in YT. Walk volume. So in software, we do this by looking at if it starts inside it, then it sets intersect t equals 0. So in this particular case, intersect t would be if we are inside it. We compute that. If it exits before it intersects, okay? If enter t is greater than or equal to 0, intersect t is equal to enter t. If 0 is not less than intersect t. So in this particular case, what we're looking for is that it intersects sometime after 0, and that intersection time is less than our max t, and max t here is set to 1. So if t1 is less than or equal to t0, discard. If t1 is greater than 1.0, discard. Let's try that. So when we're out here, reasonably responsive, we zoom in. It's still kind of laggy. Not great. Pretty bad, in fact. T1 is greater than 0. discard. We want the minimum of T1 and 1.0 there. Okay, doesn't really change anything. Now our step size, T delta is T1, so 5 times temp T dot X, T delta. If we drop this down, it gets a lot more responsive, but you can actually even already notice, well, at least I can. You can notice the quality go down. Maybe I can't actually. Oh yeah, look at that though. I'm going to zoom way in. See if that actually does change it. No, it doesn't. Okay. NDX. What happens if we drop this? It doesn't seem to really do much. Well then. So what we can do is we can also make this drop our T delta so that it's a lot, so that it's taking much bigger steps, which should get us through the grid a lot faster. And that does seem to have an actual performance difference. So let's see. Let's add our block outline. One thing I've always been a little bit curious about is what happens. I don't want a block outline, but I would like to know how many grids we move through, which would be an interesting thing to see. But I'm actually going to spend just a little bit of time now using the NVIDIA performance tool. Now, I wasn't able to get a whole lot of stuff out of this last time, but let's take a look. Go to Frame Profiler. And I want to be very clear that the reason I couldn't get anything out of it was probably my own fault. Okay. So it's loading. There it goes. Oh shoot, one thing I need to do before it really works. I need to go back into the Piglet context, and I need to say self.do update equals true, because we want it to be constantly running. So let's launch it again. So now my GPU is going to start grinding because I'm asking it to refresh as fast as it can to do the full ray tracing every single time. We zoom way in. Let's see. 4, 5, wow. 2 frames a second at best. So let's capture a frame. Then it's going to pause. Starting replay. And then it should give us a breakdown of what we are spending our time on. Now the way that the blocks group goes, you'll see, is that it does a whole lot of drawing elements. So let's go back up here. Oh, it actually, yeah, and it's doing GL draw arrays with the points. So if we look at one of these, see GL draw arrays, GL int first is 79. So it's doing a whole bunch of what amount to instance renderings. But for instance, well, in total, they are a lot. Each individual one is not that much. But we can use this to figure out, say, which grids are taking up the most time, maybe. They're sorted, not totally sure in which order, but let's take a look. Interesting. So this one took 10 milliseconds on the GPU. That one took 0.14. So we're seeing a whole bunch of these that are being drawn. That are quite strange. Now that's interesting. So this is the object that's being drawn. Let's go down here to one of these. Let's filter GL draw arrays. Wait, why is this one? So these, they're taking a fair bit of CPU time as well. These actually look weird and wrong to me. Now some of this is going to be the time is going to be a result of the textures moving, textures being bound and unbound. But this is not what I'd expected to see. All right, let's see. I'm wondering if perhaps the way I'm drawing this is not accurate. Okay, let's get back out of this. I'm going to terminate. Let's change our AMR volume rendering file to a simple unigrid rendering. So let's go back up here to examples. Let's change this one. What's it called? So if we do this, now let's say ds is equal to that, ds.fields dot gas. Do we get density? We do. Okay, good. So let's go back over here. Let's duplicate. Oops. Unigrid volume rendering. Set it to 128, 128, 128. No annotations. I'm doing the wrong one. Unigrid volume rendering. Okay. We're seeing stuff. And it's random, so it kind of looks right for a random data set. If we do projective integration, looks about right. So now let's go back over here, connect to this one. We'll say unigrid volume rendering. So we'll frame capture. Let's take a look at what our draw array elements. No, it's not draw elements. That's the GUI. Draw arrays. It's not that. Here we got draw arrays. Okay. So that looks more right. Oh, that's the wrong one though. Clearing our buffer bit. This is the one with the incomplete texture. Oh, that's interesting. That might be the, I think that's the color mapped image, so that's interesting. We'll have to fix that. Okay, so this looks pretty correct, right? Now let's resume. Okay, now let's zoom way in. We'll capture a frame. Let's take a look at our draw arrays again. Okay, maybe it's not that bad. Let's see if we can wireframe. Let's ignore the render target if we can. Interesting. Well, so I'm starting to wonder now if I've implemented something wrong in the grid rendering. No, maybe not, but it would certainly explain a couple things. do want to address this in complete mode, so we will come back to that. Let's take a look at the issue here. Which was not bound. So vertex array object. Properties not normalized. Vertex binding buffer 11. Vertex, let's see. Transform. Textures. GL texture 1D. 800 by 800, one sample, one MIPS. So this is the frame buffer into which we are rendering. This looks like our color map. You can sort of make out arboretus or whatever. And then we've got our depth component here. So what's wrong with our? Why is it not? Why is it not complete? Validate status GL false. Texture unit 1, texture unit 0, texture unit 1, texture unit 2. Interesting. This render call is using incomplete textures. Let's view the issue. Creating a complete texture. Oh. Looks to me like it's because I am doing something wrong with the MIP mapping. Let's see if we can fix that, and then I think I might call it a day. So let's take a look at our blocks, and let's take a look at our OpenGL support. Now it was only in the depth buffer. So we've got this create texture. Was it the depth buffer or the frame buffer? Render buffer storage. Frame buffer texture 2D. MIP map level normally 0. MIP map level normally 0. So let's check. Maybe it's our color map. Color map texture. No. There it's setting texture 1D. Oh, but I didn't implement the MIP mapping here. GL text storage 1D. Let's set it to 6. Let's see if that addresses the issue we're seeing. frame. And we can actually probably inspect the various different textures to see which one's the one that is missing a bitmap. Alright, let's see. Do we have any issues? One issue on GL draw arrays for GL triangles. Alright, well, let's take a look at it. Go down to textures, 6 MIPS, 1 MIPS, 1 MIPS. So let's see. Max level 1000, base level 0. Huh. Look at this one. You know what? Maybe I should be generating bitmaps regardless. Let's take a look at frame buffer. Texture. This is the binding. We don't want the binding, that's not the important part. We actually want texture 2D. Yeah. So inside texture 2D, what we want to do is we set our MIP maps. And let's set our MIP map level here to, might as well do 5. Let's see how that works. Entirely possible. I mean, I'm basically stumbling around in the dark at this point. Trying to figure out which texture is incomplete and how to complete it. Capture a frame. Still incomplete. But it's only the frame buffer and the depth buffer. So got those. Okay. The depth component. The depth component is still not generating MIP maps. Okay, so it's got to create texture. Might as well try it, right? We should be able to capture a frame right away. See any issues with it. Okay, no more issues. Let's resume, let's zoom in a bit. We'll capture another frame. Did we get any issues this time? No issues. Wow, okay. Well, that was interesting. Let's take a look at this. It was draw arrays. And if we look at this event, let's take a look at our textures. 10 MIPS, 5 MIPS, 6 MIPS. Okay, so it's got MIP maps now, but it looks like they're all kind of garbage, which, I mean, what I've seen online is that, yes, that is indeed the case. So at least now we're not seeing any issues, but it doesn't seem to have improved anything, and I guess that's fine. So I'm going to go ahead and save this. Let's go back over here, and we're going to finish up for the day. Staged changes. Minus that. Blocks. We actually probably want to update our blocks because we've got this new reset color bounds. Vertex. I don't see any differences there. OpenGL support. Got some MIP maps. Do that one. Piglet context will discard. Discard our grid position. Discard our ray tracing. And let's go back over here to our unigrid volume rendering. Get all of that. And
1 second, sweetie.
We'll stage that one.
Nap time is over. I just need to put my stickers away.
And now okay, so we've committed, and we're going to say git push origin AMR QOL. And then create a pull request. I like doing this on the command line. A work in progress of improvements for grid rendering. I'll go ahead and submit. Okay, so we've now submitted our pull request. Not totally dissatisfied with how this went. Thanks, those of you that were here. Have a good one.